This meeting is now being recorded.
So we're lucky today to have Lindsay Krall from George Washington University. She is going to be talking about back-end implications for advanced fuel cycles. So Lindsay, please.
Okay, hi everybody. I see a lot of familiar names on my screen. Unfortunately, I can't see your faces. But thanks for tuning in during your lunch hour to talk about nuclear waste. Better to deal with this now than at happy hour, trust me. So today we'll be comparing the waste management implications for several nuclear technologies in the context of climate change and nuclear security. So, as we all know, faced with irreversible climate change, mankind must drastically reduce its carbon footprint by mid-century, simply in order to maintain a somewhat hospitable environment here on planet Earth. By now, the IPCC considers nuclear electricity an essential component in a carbon-free energy portfolio. But the world's accumulating inventory of spent nuclear fuel remains a cause of concern. After half a century of nuclear energy utilization, not a single nuclear nation has managed to construct, operate, and dispose of their spent fuel in a deep geologic repository, where the safety and security risks posed by the material would be minimized. Some countries, namely Sweden, Finland, and France, have advanced their waste management programs further than others. Here in the United States, our repository program has been down for a decade, and this has left 80,000 metric tons of highly radioactive spent fuel dispersed throughout the country in wet and dry storage at reactors that are close to retirement or that have already been shut down. So even if Yucca Mountain were close to fruition, you can see that our spent fuel inventory has already surpassed the site's legislated capacity of 70,000 metric tons. And even despite the socio-political and technical hurdles posed by the task of spent fuel disposal, the US Department of Energy in 1980, the National Academy of Sciences in 1996, and the Blue Ribbon Commission on America's Nuclear Future in 2012 have independently concluded that geologic repositories are feasible and they're necessary regardless of whether a closed nuclear fuel cycle is realized at some point in the distal future. And disposal in deep mine geologic repositories remains the international standard for securing this material. So despite the consensus among expert panels, innumerable startup companies, large multinational corporations, policymakers, and philanthropists are standing behind Generation 4 reactors, claiming that with minor research and development, these would be a viable option to mitigate climate change. Among the other claimed benefits pertaining to safety and security, these reactors are said to dramatically reduce the burden of radioactive waste, sometimes to the extent that they would obviate the need for geologic repositories. Making no comment on the RD&D efforts that would be required to deploy such a fleet of advanced reactors by 2050, we're going to deconstruct the latter claim regarding the waste reduction benefits, so that you can understand why these claims are grossly misleading. Sorry if this is patronizing, but it may be worthwhile to give a recap of the basics of nuclear electricity. This is derived from the heat that's released when the nucleus of an atom, after having absorbed a neutron, splits. This implicates the generation of fission products, which are two lighter elements whose mass approximates that of the fissioned uranium atom, in addition to 2 to 3 neutrons that may go forth to propagate the fission chain reaction and or generate additional fissile actinides such as plutonium. So you can see that in red you have the fission products, and some of them are relatively short-lived. These include cesium and strontium, which are a cause of concern after a nuclear accident because of their very high activity. And then in the intermediate term, you could say, up to say 100 or up to 1 million years, the actinides dominate the activity of the waste, but they're also long-lived fission products. So the premise of advanced fuel cycles is to enhance the fission of the actinides, which are bred in the neutron absorption reactions, so that eventually only fission products would be destined as waste for geologic repository. To achieve this requires that the fissile actinides are separated from the short-lived fission products, which would otherwise serve as a passive radiation barrier that would deliver a lethal dose to an intruder trying to divert the material. This reprocessing might increase the efficiency of atomic energy extraction, but it also poses a proliferation risk in that the separated fissile material is easier to divert. All right. So you can see that if you were to remove the actinides from this decay scheme, you would have mostly cesium and strontium dominating the activity, and that's for approximately 300 years. So that's where this claim that advanced fuel cycles would reduce the longevity of the nuclear waste comes from. So among the nations that maintain nuclear waste management programs, the most popular disposal concept is some rendition of the KBS-3 repository designed in Sweden. This is a multi-barrier system that accounts for the array of half-lives and chemical behavior of elements present in the spent fuel. In the short term, the spent fuel can be removed from a cooling pond and directly packaged into a canister destined for the repository. In that the spent fuel is clad in zirconium and stacked into rods that are bundled in a fuel assembly. The packaging can be done on an industrial scale while minimizing worker exposure to radiation, which again is most intense over the shorter 100-year time span. And then the material for the canister is selected so that it's thermodynamically stable or chemically compatible with a geologic disposal environment. For instance, the corrosion rate of copper is very slow in anoxic environments, such that a 5 centimeter thick copper canister should last for tens of thousands of years in anoxic groundwaters. This is evidenced not only by laboratory and field experiments, but by natural analogs as well. And this time horizon extends past that of the peak fission product radioactivity. In case the canister fails prematurely, the repository is sited in anoxic groundwater at great depths in the bedrock, so that, like the canister material, the spent fuel waste form, which is predominantly uranium dioxide, is chemically stable. The spent fuel matrix, having a flexible crystalline structure, also incorporates most of the actinide elements and fission products as well, through strong ionic bonding. Thus, dissolution rates of spent fuel, and therein the rate of radionuclide released from the repository near field, is slow. And the repository should be located at great depths. This one is at 500 meters, where groundwater flow rates are slow, and that oxygen of atmospheric origin does not penetrate the system. And this also ensures that radionuclide transport rates in the event of fuel dissolution are slow. So after a repository has an adequate multi-barrier system and is sited appropriately, most repository safety assessments indicate that the most significant long-term risk is actually posed by the long-lived fission products, and not as much the actinides and their daughters. The daughters of uranium-238 are also released, but these exist in nature anyways. So you can see the 238 daughters in purple, the fission products in red, and the actinides, which are the lowest risk over the long term, are in green. So the argument for burning plutonium in advanced fuel cycles seems to stem from the situation at Yucca Mountain. Since the now abandoned proposed host for the U.S. repository was sited in an oxidizing or oxygen-rich environment above a freshwater aquifer, plutonium, uranium, and other actinides did indeed pose a risk to future populations. The risk was compounded with, rather than exchanged for, that of the fission products, activation products, and daughters in the uranium series. But since I'm only allotted 45 minutes for this presentation, we're not going to discuss additional geologic issues at Yucca Mountain. So on to molten salt reactors. The principal difference between these and water-cooled reactors is that the designs typically call for the fuel to be dissolved directly into a bath of molten fluoride or chloride-based salt for use with thermal and fast-spectrum neutrons, respectively. The reactor was conceptualized in the mid-1900s for application in aircraft propulsion, but given the radiation shielding requirements, the concept never took off, and so was revised to meet societal demands for terrestrial energy. For some years in the 1960s, Oak Ridge National Lab conducted the molten salt reactor experiment, and this showed that it was possible to fission isotopes of uranium in a bath of hot salt, but the reactor that Oak Ridge hoped would achieve the net breeding of fissile material was never demonstrated in an actual reactor. So recent proposals hope to bring the breeder reactor model to life, and they call for very similar systems and components as the molten salt reactor experiment at Oak Ridge. This includes a graphite moderator, a dump tank, here you can see down here, and an off-gas system, which is up in the right-hand corner of this figure. So the off-gas system is needed to vent volatile fission product poisons, including isotopes of xenon and krypton, out of the reactor vessel so they do not consume neutrons that would otherwise propagate fission reactions. However, as these are vented, some decay into isotopes of cesium and strontium and get trapped by filters in the off-gas system. But those gases that do pass through the system are supposed to be collected and compressed into bottles, then stored and disposed of as gas. But in addition to the noble gases, various other elements that are chemically incompatible with the salt migrate into the off-gas system, along with longer-lived actinides that migrate into the off-gas system because they get attached to particles of cooled salt. So the Oak Ridge reported that these off-gas filters ultimately contained an array of short and long-lived radionuclides with a composition similar to that of high-level waste. So considering that this contains highly radioactive material resulting from the reprocessing of irradiated nuclear fuel, as dictated in the requirements, this requires geologic disposal and is neglected from the waste generation estimates provided by the developers. But even given this off-gas system, molten salt reactor designs still call for this blue box over in the left, which is a chemical processing plant. And this is either online chemical processing or at a separate facility. And only after separating fissile uranium-233 or 239 plutonium isotopes and reintroducing them to the reactor can cited burn-ups of 90 to 250 megawatt days per kilogram being achieved. However, the latter figure would require high-assay, low-enriched uranium, which is not used in current light water reactors. So if you use 5% enriched uranium and you forego the chemical processing, then burn-ups are only 26 megawatt days per kilogram, which is about half that of current light water reactors. So if you're looking to compare waste generation among fuel cycles, this megawatt days per kilogram metric is inversely proportional to the mass of spent fuel produced per unit energy extracted, considering only the heavy metal and fission products for the fuel, rather than, a processed waste form that's suitable for a repository. So if we're comparing apples to apples, i.e. a once-through fuel cycle with low-enriched uranium, molten salt reactors seem to generate twice as much heavy metal per unit energy generated compared to a standard light water reactor fuel cycle. However, as previously explained, the fission product composition of the waste streams are roughly the same for each fuel cycle, regardless of burn-up. And as opposed to the mass of spent fuel, it is actually the fission products that dictate the volume and barrier requirements for most geologic repositories, with Yucca Mountain again being the exception. Fission products are the main source of heat, so they dictate the spacing of the spent fuel canisters throughout the rock volume, so that the canisters are distributed so that the groundwater does not boil. Okay. So given that these reactors would entail significant volumes of salt in need of disposal, we would need to look for natural analogs to understand the type of environment that this material would be stable in over geologic time. But unfortunately, uranium tetrafluoride and uranium tetrachloride salts do not exist in nature. This is probably because they are chemically and radiolytically unstable. One precedent regarding the disposal of uranium fluoride compounds was set in the 1990s by the NRC, who decided that the DOE should not dispose of depleted uranium in the form of uranium tetrafluoride. This was a relic of enrichment, so it was depleted uranium. The uranium fluoride salt dissolves rapidly in groundwater, and let's say if one canister fails prematurely, then this uranium tetrafluoride would dissolve and it would simultaneously generate hydrofluoric acid. And this acid would prompt a positive feedback loop by enhancing the corrosion of otherwise intact canisters, since the hydrofluoric acid is a very corrosive substance. Given such issues, the near criticality accident at the shut down molten salt Oak Ridge reactor was unexpected but not surprising. When the experiment was terminated, the used fuel site salt was drained into those dump tanks I pointed out earlier. And since in these tanks the salt was in a subcritical configuration, the operators decided that it would be safe to wait some decades for part of the radioactivity to decay before attempting to decommission the facility. However, the radioactivity can induce complex responses in materials, so that as the radiation damage accumulates, the chemically bonds are weakened. The bonds in uranium tetrafluoride, being very weak, were eventually broken by the subatomic particles flying around in the tanks, and this caused the generation of uranium hexafluoride and fluorine gas to form, the former of which accumulated in sections of the off-gas system. Maintenance engineers recognized that uranium hexafluoride was being lost from the tanks and that this was enriched in fissile uranium-233. But as long as water wasn't present to moderate a fission chain reaction, it was presumed that this would be acceptable. However, the fluorine gas interacted with moisture in the dump tanks, and so this formed hydrofluoric acid and corroded the pipes and allowed more water to ingress. Given the remarkable safety risk posed by this situation, it required prompt attenuation, so it was complicated by the high radiation fields emitted by the salt. So the DOE decided that the best way to extract the remaining fissile material and other actinide from the dump tank was by bubbling fluorine gas through the system. This formed volatile uranium hexafluoride that could then be trapped by filters in the off-gas system. Conveniently, this approach, or the fluoride volatility method, is the same that was and is once again being proposed for the reprocessing of used MSR fuel salts so that its fissile material can be separated and reused. Since having extracted the uranium, the DOE has converted it to uranium-oxide, probably mixed with depleted uranium, and suggested that it be sent to the Nevada test site and disposed of as low-level waste, despite its classification as special nuclear material. As for the fission product-laden sludge in the Oak Ridge dump tanks, it's still there. It's not really clear what the DOE plans to do with it. Sending the tanks to WIP and on-site entombment have both been proposed. But
do you want to say what WIP is, in case people don't know
WIP
what WIP
is the Waste Isolation Pilot Plant in New Mexico. It's an intermediate level waste repository that the DOE operates. Okay, but the details regarding either of these options and the implicated feasibility and safety aspects have not been shared with the public. Hopefully my Freedom of Information Act request will provide some more details there. To put the experience at the molten salt reactor experiment in perspective, this was an 8 megawatt reactor, which is orders of magnitude smaller than the MSR designs being proposed today. And onto the second most popular Generation 4 design on the market, the sodium fast breeder reactor is another concept that dates back to the early 1900s or to the early 1950s. The DOE operated 3 such fast reactors and today plans to build another similar test reactor in Idaho. This reactor calls for a core that is enriched, typically up to 20% in fissile material, being plutonium-239 or 235 uranium. This is supposed to fission and produce heat plus neutrons, which go forth to generate 239 plutonium in a blanket of 238. The bred fissile material is then processed, often through an electrochemical approach called pyroprocessing, then eventually purified and used to refuel the core. Developers suggest that the pyroprocessing systems be co-located with the reactor. So unlike the molten salt reactor, the fast breeder reactor fuel pins are not directly dissolved in the sodium coolant. Rather, most of the designs promoted by the US companies call for sodium bonded metallic uranium fuel. This was developed during the late DOE liquid metal fast breeder reactor program. Here you have a diagram of the fuel, and you can see that it was hand-drawn several decades ago. This is clad by stainless steel as opposed to zirconium, but designs in the rest of the world typically call for MOX fuel rather than metallic uranium fuel utilization. However, DOE posits that the sodium bonded metallic uranium is less reactive, less chemically reactive if it comes in contact with the sodium coolant. However, DOE also heralds the fuel for its compatibility with pyroprocessing. Burn-ups in a once-through fuel cycle, in theory, are higher than for light water reactors. TerraPower is hoping to exploit such a once-through fuel cycle, wherein the blanket, after having bred sufficient plutonium, would be shuffled inward without needing to be reprocessed. Neutronic simulations indicate that burn-ups of 300 megawatt days per kilogram might be achieved if high-assay, low-enriched uranium is used for the initial core loading. But among the technical challenges associated with the design, the fuel cladding in such a fuel cycle would be damaged before such high burn-ups are reached. It's a very extreme environment with fast neutron radiation, damage by fast neutrons, also heat and corrosion. So given the mechanical limits to the cladding, burn-ups of 200 megawatt days per kilogram might be more realistic, according to experience at the DOE test reactors. Compared to thermal neutron reactors, fast neutron reactors can breed and fission plutonium more efficiently. So energy security goals of the mid-1900s motivated the development of these plutonium-fueled reactors because uranium resources were thought to be scarce. Many nuclear countries began reprocessing the fuel from their water or graphite moderated reactors so as to stockpile plutonium that could be used to fuel a future fleet of fast reactors. But given that abundant uranium was soon found, that nuclear energy was not as widely adopted as anticipated, and that the development of fast reactors was plagued by issues such as sodium fires, there now exists a legacy of separated civil plutonium, which is weapons usable and has no passive radiation field to secure the material from intruders. The issue is particularly acute in the United Kingdom, who has been considering to utilize the unproven GE PRISM technology to fission this separated plutonium. GE Hitachi has suggested that the reactor can be used in a once-through fuel cycle to burn the plutonium, although such a scheme would actually generate a net increase in plutonium. Furthermore, it's not clear that this reactor can be utilized in a once-through direct disposal fuel cycle. In decommissioning the experimental breeder reactor, Idaho National Lab set a precedent with important sodium-bonded waste management implications. The material is classified as pyrophoric in that it reacts violently if exposed to water. Thus, the spent reactor fuel cannot be directly disposed of in a geologic repository. The DOE decided that the only way to deactivate the fuel was through electrometallurgical treatment. This calls for the same systems as pyroprocessing, except that a slight modification is made to the electrolyte salt used in the process. So this is a very involved process. You can see a lot of components become contaminated along the way, and so all of this would be considered intermediate level waste, as is typical for reprocessing operations. So DOE is decades and billions of dollars behind in treating the experimental fast breeder reactor waste. FOIA documents recovered by Ed Lyman indicate that meanwhile the spent fuel in wet storage is degrading. In at least one case, the fuel showed that a pyrophoric reaction had occurred between water and the metallic fuel element. This was following corrosion of the stainless steel cladding. So it seems that the waste is literally burning. The notion that this technology is needed simply to prepare sodium-bonded fuel for disposal has proliferation implications, as well as implications for exporting a technology that can easily be modified to separate fissile material. So, concerning advanced policies for these reactors, there's always a complaint that reactor licensing is entirely favored for light water reactors, and it does seem to be true that the licensing process is light water reactor specific, in that there's no requirement that the developers need to prove that the spent fuel is stable over the long-term time period. There's really no long-term requirements on the spent fuel at all in the reactor licensing process. However, we do have the Continued Storage Rule and the Nuclear Waste Policy Act. These form the basis for new reactor construction. The Continued Storage Rule says that the spent fuel is safe stored on the surface until a geologic repository becomes available, and this was decided in the context of the cancellation of the Yucca Mountain project. So you can build nuclear reactors even though we don't have a waste disposal program. However, for the environmental impact statements that support the proposition that the fuel can be stored safely on the surface and in a geologic repository, considered oxide fuels. So these were modeled in the simulations of fuel transport and behavior. Another issue is who's going to be responsible for the treatment aspect. Will it be the Department of Energy, as under the current Nuclear Waste Policy Act, or is it going to be the utilities, or, I don't know, the lowest bidder? So it looks like the back-end infrastructure for these reactors are going to be quite costly. The waste reduction that the vendors are quoting use irrelevant metrics. They're formulated around volume, actinide mass, and long-term radiotoxicity, whereas in the geologic repository backend aspects, we're more interested in the mobility of radionuclides in the environment, the heat output as, provided by the fission products, and you also need to process, say, even if you're left with a mass of fission products, those are still going to be needed to be put into some sort of stable matrix, such as in France, those are vitrified. So ultimately you have a larger volume of material than just the fission products. Okay, in addition, the metrics assume that closed fuel cycles with reprocessing are adopted. And since you can't fission fission products, then as has previously been determined a number of times, advanced reactors will not obviate the need for geologic repositories. If the advanced reactors are deployed in a once-through fuel cycle, probably the burn-ups will be too low to justify the bloated waste treatment costs. There's going to be RD&D required to develop the treatment and conditioning facilities. And then these facilities are also going to generate intermediate level waste that needs to be disposed of. In addition, like the cores of the reactors need to be decontaminated. So, for instance, the molten salt reactor that has all the radioactive material dissolved directly into the coolant is just going to be coated with radioactive elements. So these cores will need geologic disposal. And Terrestrial Energy, a Canadian company, is promoting cores that only last for 7 years. So it seems that there are going to be a lot of cores that need to be disposed of. It's not really clear what Terrestrial plans to do with the core after they remove it from the site. But anyways, you're also going to need to decontaminate the fluoride, salt, and sodium coolants. With water-cooled reactors, this is pretty straightforward because you can just filter the water and remove most of the radioactivity. But fluoride and sodium are going to require much more intensive chemical processes. And then there's filters from the off-gas systems, either as part of the molten salt reactor or as part of the electrometallurgical treatment facility for the sodium fast reactor. And these filters are going to be classified as high-level waste. Not to mention the proliferation risk. It's kind of concerning that the DOE set this precedent that the only viable fuel treatment options are extensions of advanced reprocessing technologies. They've already proven that it's pretty easy to modify these treatment facilities to reprocess the waste or extract fissile material. So you can co-extract plutonium with uranium as opposed to in a once-through fuel cycle. Say GE would suggest that the plutonium remains with the fission products in the salt bath, the pyroprocessing salt bath. But by just changing minor aspects of the chemical condition, you can co-extract plutonium with the uranium. And then this would be pretty straightforward to separate from the uranium, and you have a weapons usable material. So safeguards are going to be an additional cost, and no one's really asking whether this is a good technology to export. Well, a lot of people are asking it, just not the policymakers that are funding the reactors. And all these proliferation risks are in addition to the plutonium that's already been separated in the name of advanced reactor development and needs to be dealt with. So is it really likely that these reactors and treatment/reprocessing technologies will be available by mid-century? It's kind of an issue that the treatment and reprocessing is not only needed for the geologic disposal of the waste, but they'll be needed to just secure the waste at the surface, because all the fuels are violently or really easily dissolved by water, or they can burn. So it's also worth pointing out that waste isn't an obstacle to light water reactor expansion for the continued storage rule. And there are several viable repository concepts, but there have been social political failures that some countries have not surmounted. Also, the economics of nuclear is challenged by natural gas. And advanced reactors at current estimates are barely cost competitive with light water reactors, but if the waste management costs were to be considered, then they would very unlikely be competitive. A lot of the vendors are actually assuming that they'll get a credit for reducing waste management costs. That is, they expect the DOE to pay them to collect the spent commercial reactor fuel that is currently at the reactors. So yeah, that's that's something, that's a positive. Okay, so references for further reading. This presentation was made from an article that was published in the autumn, and also there's a new report out on the reset of America's nuclear waste management strategy, and this has a lot of good pointers for how a geologic repository program might be restructured so that it can be more successful. And I'm also looking into deep boreholes for nuclear waste. The vendors that have acknowledged that they'll produce high-level waste suggest that they can easily deposit the high-level waste on a deep borehole. But to state it simply, this is not a miracle cure for waste management woes, and that was said by the Electric Power Research Institute. Okay, so you tell me, why not transform nuclear waste into wealth? And many thanks to my funders and George Washington University, and I also benefited from discussions with the researchers at Sandia National Lab. And I'd be happy to take any questions.
Okay, thank you. We've got about 10 minutes, and I noticed that Ramana has a question. We'll get to him in a minute. If others have questions, let me know. I wanted to start out with something that, given the problems that you've talked about here with waste, with non-proliferation concerns, things like that, it's a little surprising that these just that there's so much enthusiasm about these systems. And I'm wondering if that's partly because they're still early enough in research and development that people are simply arguing that those problems will be solved eventually and that the benefits will outweigh those problems, or I mean, what's the dynamic that's sort of pushing these ahead?
I think there's a great fear that the nuclear enterprise is going to collapse due to the major economic issues that it's facing. So, you know, Westinghouse has declared bankruptcy, and so a lot of this is like, you know, saying, oh, light water reactors are unsafe, they have all these issues, and so these advanced reactors are better than light water reactors in all these respects. And like, if you look at design basis failures for light water reactors, then sure, maybe there are some benefits to advanced reactors, but there are a lot of, you know, aspects that just aren't considered in their, like, you know, engineering for their safety. And then from the policy side, I think there's a lot of motivation to be, like, competitive with, say, China and Russia and sort of put an advanced reactor to market before, you know, the other countries. So there's a competition aspect, and there's a hope that, like, developing countries will adopt nuclear because advanced reactors, they're saying that they're plug and play. So you can just build a reactor and then it operates itself. So yeah, it's not about climate change, I guess you could say.
Okay. Let's see. Raman, I've just unmuted you. Do you want to ask your question?
Sure. Hi, Lindsay.
Hi, Raman.
So as much of what you've said is based on U.S. regulations for dealing with waste, and I was curious how other countries might deal with these new waste forms, and if their regulations are easier to deal with or more difficult. I know that you have a lot of experience with Sweden. So any thoughts on that?
Well, in Sweden, let's say there's more accountability for the implementer of the waste management program. So let's say Vattenfall, the Swedish utility, they are the implementer for the waste repository rather than, say, the government, as in the U.S. So when you have the utility needing to think about how to deal with the waste from advanced reactors, then I think if they're going to be held accountable for the waste, then they're going to be more realistic about what is going to be required to dispose of it, and they're going to, you know, like in Canada as well, this is the case, and the Nuclear Waste Management Organization reviews advanced reactors every year, and they compare it to what's required for repositories for oxide fuels, and it's not clear that they'll be willing to build an advanced reactor. And in addition, like the other countries that are developing the sodium fast reactors, they're using mixed oxide fuels as opposed to the metallic fuels. So probably mixed oxide fuels will be easier to dispose of in that they are not flammable, although there are some potential, you know, mixed oxide fuels are not necessarily preferable to pure uranium-oxide fuels. So, internationally, I think.
Yeah, my question was also in the safety realm when it comes to licensing reactors. There's an argument that many of these advanced reactor vendors offer, which is to say the NRC is excessively strict. They have they're only geared towards light water reactor licensing and so on. And therefore, we know we need a more flexible regulation regime. I'm wondering whether there's a similar kind of comment made about the waste regulations, for whether the regulation scheme in the U.S. is quite strict.
I do not think the waste regulation in the U.S. is more strict than elsewhere.
Okay. Thanks.
Yeah.
We can talk offline.
Okay. Stephen Young had a question. Stephen.
Thanks, Lindsay. So let's pretend that you work for the Congress and you are the key appropriations staffer who gets to decide how the DOE spends, say, $1 billion on nuclear power. And you can spend it on any piece of nuclear power equation, on safety, on disposal, on advanced reactors. How would you spend $1 billion on nuclear power if you were DOE? You can fund other companies, you can fund private business, you can do whatever you want with that money. What would you do with $1 billion for nuclear power research?
I mean, I would look into the geologic disposal, I guess, try to fight more, appropriate repositories, and but at the same time, the DOE doesn't really have that choice. So I would encourage Congress to, look more closely at the Nuclear Waste Policy Act and see if we can reset our program so that it can be more successful, looking at the successes that have been experienced in other countries. But I mean, if there was unlimited money to spend on energy research, I think an easy way to get that would be from the defense spending. That's where most of the research money goes, so not really into energy. So,
Stephen, I assume this is not a purely rhetorical question, that there are people in the appropriations who are going to be looking at this.
Yeah, and the questions are, how much should we be spending on advanced reactor research versus safety versus disposal R&D funding, and are there questions that are more, where you get more value for your spending?
Okay. Well, I think that light water reactors are sufficient, and you can study ways. There's still a lot of progress that can be made, and that those technologies pertaining to fuels that are more tolerant of accidents and lower dissolving than uranium dioxide fuels. So I think if you, a lot of the advanced reactor motivation is to make nuclear competitive with other energies. And I think a helpful way to, a way to help nuclear energy would be through, say, a carbon tax or so. Yeah, I don't know if that is helpful.
I don't see anybody else in the queue, so I had one last question that I wanted to ask you, and then we can wrap up. You had mentioned that Yucca has an oxidizing chemistry in the ground, which surprised me given some of the things you had said. Can you say something about how that was chosen, how that decision was made? It doesn't sound like the environment you would like to have for a repository.
Well, the decision was made by Congress, and not the technical experts. So, I mean, this was in the 1980s. It was before a lot of the research on nuclear waste disposal was conducted. like the natural analogs, a lot of that work was done in the 1990s. So maybe in the 1980s, it wasn't, appreciated how much an appropriate geologic environment can help you. And this was also before like the more successful concepts were introduced. So there were all sorts of different ideas being thrown around, and the U.S. sort of went full force at one idea without really, diversifying a research program. A lot, it was politically motivated. Nevada is pretty weak politically.
So it sounds like part of what you're saying is that the understanding of the science has moved on since that decision was made. But given the oxidizing environment, is that a particularly bad issue that people now have to reconsider, or would you say that's something that people could deal with?
I think the oxidizing environment, it's hard to, explain to, like the public in sort of, a subjective way, a non-quantified way, like why, the spent fuel should be stable over the long term. You can't really refer to natural analogs. And, at first it was thought that Yucca Mountain had like really, really slow groundwater flow rate, but as the project progressed, they realized they were faster than expected, so that made the oxidizing, the corrosion occur faster from the faster water flow rate. And so like we ended up just with a really, really engineered repository design. They had to introduce a titanium drip shield just so the dose regulations could be met. And the drip shield is like absurdly expensive. It's kind of a joke in the international community how expensive it is. So say you have an oxidizing environment, if you want to prove long-term safety, then you're just going to have to spend a lot more money if you're not getting, passive benefits.
Mm-hmm. Okay. Well, thank you very much. Ramana is encouraging you to write an even longer article than the bulletin article, and I think that getting this discussion going is obviously important. So thanks again, and we will post a recording of this for people that weren't able to make the talk today.
Okay, thanks for organizing this, David, and thanks everyone for tuning in.
Okay, goodbye.
Bye now.